Welcome to what I'm going to be talking about. I'm glad so many people seem to be interested in it, at least so far. Curious, have any of you seen Jeff Hawkins talk? He talked here a while ago. Okay, a few. Yeah, he's a guy I worked with at Redwood Neuroscience Institute. He's better known for having invented the Palm Pilot. And there's a certain degree of overlap between what I'm talking about and what he did. I'm going to get way more technical and mathematical. But we have a lot of common approaches, so something might seem familiar. What I'm interested in is how the brain works. I think a lot of us are. The brain is arguably the coolest mystery left in science. It's very compelling because we each have one, and it's who we are and it's what we live through. But it's also a much more approachable topic than you'd think of. It doesn't depend on quantum things or gravitational physics or anything. It's macroscopic, thermodynamic. It's in the right scale to investigate. It's just electrochemical. It's a bunch of circuit elements, really. It's cool if we understand it because of who we are and because it's got so many practical applications. If we figure out what it is which is going on inside our heads, or even inside the heads of mice or cats, then we will be a long way toward the holy grail of real machine learning and toward robotics. Being able to hook up all the sensors and the compute power and the actuators to be able to do something coordinated and sensible. So this is a really cool thing to approach, and I think we're on the cusp of having the grand unified theory, the E equals mc squared of brain algorithms. And when we get it, I think it will be a generic algorithm. It's not going to be one little piece for color vision and one piece for binocular vision and one piece for speech and one for music and so forth. It's going to be a single thing which covers all of those. A sort of a generic algorithm, probably the mother of all algorithms in terms of its usefulness and its impact. And we have an existence proof because we're all carrying around something. We are capable of learning practically anything. We don't even really pay that much attention to how we get our cues from our visual system or our auditory system or our balance and so forth. We seamlessly put them together, and we can fly fighter planes and write computer programs and all kinds of other crazy things which you wouldn't think of for a mammal with a bunch of straightforward nerves coming in and a bunch of other motor nerves going out. So there is something cool going on. I'd like to talk about how to get there from here. There are really two questions people tend to ask about how the brain works. One is a question of circuitry, and one is a question of algorithms. The circuitry part is by far the most traditional way of doing theoretical neurobiology, brain science, whatever. What is a neuron? How are neurons connected? How do they talk to each other? How do they send their signals? What does a group of them do? And what happens inside a neuron? What's its computation? Ion channels, sodium, potassium, dendrites, second messengers, all kinds of electrochemical stuff inside. All of those together are the traditional way of approaching it. And I'd say it's the wrong way of approaching it. In great part because the data is just so multifarious, ambiguous, hard to interpret, tangled, nasty, and just not worth building a theory on. It's interesting stuff. I spent almost all of my academic career doing that. I discovered some really cool things about what happens inside neurons, and I'll talk your ear off if you want to talk about how difficult it is to really understand the brain from the circuit level. But for me, that's not where I want to push things. The other part is the algorithms. That's where I think interesting stuff is going to happen. And that's where I've spent, my last 10 years as an algorithm hacker, programmer, software engineer, software architect, biophysicist, things like that. And that's the mathematical part. It's not what the circuit elements are. It's what mathematical operations do they do? How do they represent things, store them efficiently, transform information, do the computation? What's the statistical inference going on? Is it Bayesian? Is it quantized, continuous, manifolds, metrics, all that kind of stuff. The mathematical part is the part which doesn't have to wait on experiment. It doesn't have the same ambiguities as experiment. And it's something which, if you get it right, has applications this afternoon rather than 10 years hence. So I wanted to approach this more as an algorithm problem. with the three pieces, I'm only going to talk about one of them, but the three pieces of how to approach the brain as an algorithm are, first of all, what's the problem space? You don't hear that much about it, but if a brain is going to make sense of sensory data, of 1 million pixels coming in, or sound coming in at 10 kilohertz resolution or something, tactile from all over the body, proprioception, whatever, if the brain is going to make sense of this stuff, what is a pattern? We say brain does patterns, but is a pattern a linear manifold, a nonlinear manifold? What kind of dimensionality does it have? What kind of continuation in time? We need to understand the input space before we talk about what to deal with it. Second question, of course, as a software architect, is what is the modularity of this? We can't solve it all in a go. We have to break it down into pieces. So what would be a module for a chunk of the brain to deal with? And what is the API between modules? How do you make sure that they're robust when they're hooked together, that the whole thing is scalable? So that's the connection between modules, which is a really good question. The piece I'm going to talk about today is a subset of that. It's what happens inside a module. You've got one piece of the brain, this square centimeter of cerebral cortex, say. What does it do with its inputs? What cues does it have to do inference? What are its outputs going to be? How can it stitch them together, generalize properly, that kind of thing. That's where I want to get into some excruciating detail, or at least hackdom, today. But before getting there, one thing about the method which distinguishes this approach from a lot of academic approaches. Even though I'm speaking of this as a mathematical problem, I don't think the answer is a handful of equations in a paper somewhere. I don't think the answer is some sort of architecture which looks like the brain, or some set of outputs which looks like how brains work. I don't think looks like is sufficient. I think the answer is more like something which works. We need to build a system which functions, which does something proper perceptually, which generalizes in the right ways. And then we'll have a hunch that we're on the right track, because nature can't let us do that unless we're doing something right. And of course, we'll have a working product, whatever that means. But in order to get there, in this kind of the nasty mother of all algorithms, involves understanding something about algorithm development. Algorithms are hacked, they're fiddly, they evolve, they iterate. They don't just come out born whole on the page. There's a process involved with them, a process which involves sometimes open source, involves teamwork and benchmarks and revisions and so forth. And I mean, I shouldn't be saying this to you. Google has arguably the world's most sophisticated and valuable algorithm, and you know how to develop it, and you know that it's more than just PageRank now. I don't know how much more, but I know it's more than that. And it involves questions of sorting and scaling and clustering and data access and representation and storage. Making something work has a lot of engineering questions in it, all of which are theoretically interesting. And that's the aspect of brain algorithm development, which I know is lurking in the background, even though I can only talk about a tiny chunk of it now. Where we are in this process is, I think, in 1903. We don't have airplanes yet. And I'm not interested in writing a journal article about the theory of airplanes. I'm interested in going to the sand dunes of North Carolina and building one. I think that after you have built something which gets off the ground, however poorly, everybody can join the team and make it better. But what we need is a reference implementation. We don't need a theory, really. So I will try to hack my way through a little piece of this and maybe convince you that even if this particular hack isn't a very good one, maybe it's on the right path. There are lots of other people who have done pieces of this. I'm not going to go into them. Lawrence Wiscott did a large chunk I'll be talking about. People like Jeff Hinton have done some amazing work in this field, and with a lot of these hierarchical modules over time. Rao and Ballard have done some of the work with temporal prediction, which they built on something I did, and I'm building on stuff they did, and so forth. I'm not going into name dropping. I just want to see if we can focus on the content for now. So let me see if I can make this work. Let's start with a few simple observations. I'd like to just make the claim at the level of mice and cats and people that all cortex is alike. This cortex is the outside part of the brain here. It turns out that every chunk of it looks the same. You know, a mouse looks a bit different from a human, but the part of a human which does body awareness looks the same as the part which does vision or verbal memory or action, emotional planning, speech recognition. It's all the same circuit. And they're wired together in a reasonably common way, hierarchically. Some parts are sort of low level. They deal with the raw sensory inputs, eyes, ears, and so forth. Other layers stitch together some of those. The ones up at the top are sort of the frontal cortex, the part we claim does the thinking and the planning. They're really wired up that way. These guys talk to each other in a stereotyped way, just as they have stereotyped internal structure. The other generalization I'll make is that essentially all of this part of the brain, all of the cortex, learns from scratch. Now, of course, you know babies start out with no coordination and they don't understand speech and they can't really make too much sense of what's around them. But there are a couple other, even more powerful indications. One is that in someone whose eyesight is gone from birth, they've got this chunk of the brain, the occipital cortex, which normally in most of us does vision. Well, it's lying dormant. These poor people don't have vision. Well, what does it do? It winds up doing something else. It not only deals with acoustics, it winds up dealing with a high level of abstraction. It does verbal memory instead of low-level vision. Same circuitry, completely repurposed. Likewise, or maybe contrary-wise, if you find some poor soul who at birth is missing the left temporal lobe, which usually does speech, they will speak. Some other part of the brain will take over that task. So they're missing 10% of their tissue, maybe they're kind of 10% worse on everything. But it seems a highly malleable, non-specific substance, whatever it is that these pieces of cerebral cortex do. So let me condense this into a sort of cartoon, and then I will do cartoons within cartoons. The cartoon here is a hierarchy in which at the bottom level you have a very high dimensional input stream, which is changing pretty quickly. Each one of these things, think of it as a pixel, but it could equally be from the ears, is changing very fast. No one of them is constant, even all of them together are not constant, or even slow. So it's high dimensional and high bandwidth. And each one of these modules I'm drawing in this faction takes a bunch of high dimensional stuff, kind of compresses it into a smaller dimension, and now you stitch together that first row, and you've got another high dimensional signal, which perhaps has correlations and structure in it. That now gets put together by the same kind of algorithm. So you basically compress your data all the way up a hierarchy until at the top you have something which is in principle less structured, more independent, more representative of the outside world, and a kind of abstraction. You know, you're thinking of a dog or a car rather than pixel 27. And it's something which is a little more persistent. Pixel 27 may go on or off, but presumably the dog hangs around for a few seconds. So you are basically finding things which are invariant over space and over time. And that's the purpose of the whole thing. And it sends back signals. So I've drawn arrows in both directions. So if you have some idea, a Bayesian prior, about what sort of thing one module is going to expect, that module can accept that and perhaps expand it out to a more particular representation and expand it down. So you've got a kind of a Bayesian belief tree here, except that it's running across time and it's having to learn a lot of its own stuff. But this is sort of the overarching view of a sensory brain. I am completely leaving aside motor motion. I'm even leaving aside the notion of surprise detection and novelty, just to make the scaffolding where we can start to get something done. Those other things matter, but I think we can do something without doing those first. Today I want to talk about just one piece of this. What is inside a single one of these modules? Now I'm calling this, my own notation, I'm calling it a compressor. It compresses data. It takes something like pixels at the bottom and puts out something like JPEG at the top. Or it takes in pixel streaming and puts out MPEG-4. Or it takes in audio and puts out MP3. The trick is it has to learn by itself. You don't even get to tell it whether it's going to be an MP3 recorder or an MPEG-4 encoder. It has to look at its input streams, figure out what the patterns are, figure out how to represent them, make the abstraction, the compressed representation, and in the process, it needs to be able to go backwards to take the compressed version and re-inflate it into something which makes sense at the high dimensional pixel level. And that last part, that blue part, is what I'm talking about today. So the questions are, first of all, letting pixels be a stand-in for any high-dimensional sensory signal. How do you turn the pixels into the abstractions? Just how do you do it? Second, how do you learn to do it without anybody telling you what you're supposed to do? And, most importantly, how can you take that compressed version and reflate it, again, without supervision? So let me jumpstart us with a technique which was published a couple years ago. I think it's brilliant. I did not invent it, and I'm not going to really tell you how it works. Just take my word that it does work. It's called slow feature analysis. And what it does is it looks at a bunch of different quickly fluctuating high-dimensional signals, such as pixels in an image, and it looks in the space of all second-order polynomials of those and tries to find those polynomial functions which change slowly. So if your pixels are doing this, it tries to find a polynomial which does this. It involves principal component analysis, variance reduction, minimum eigenvectors, and stuff like that. I can go into it later if you really want. Just trust that it works, because that's all we really need. It finds a handful of cool polynomials as a function of a much larger dimensional input space. And these polynomials tend to be more constant over time than the individually fluctuating inputs. So that's what we're starting with. Let's just assume that's already worked. Those are the S functions. Problem is, and this is a very deep problem, I think ultimately one of the hardest problems in this branch of brain science, you can't invert that. First of all, it's a bunch of arbitrary polynomials. You can't just run around inverting these polynomials of umpteen functions. Second, it's ill-posed. You've got one function of 100 inputs. You can't determine every one of those 100 numbers from this one number. That's impossible. And yet we need to do it. This whole hierarchy I'm talking about requires that we invert the uninvertible. We go from a low-dimensional signal and create a high-dimensional one, in general, in a generic sense. How are we going to do that? We hack, or at least I hack. You can do the math. I'll just plug along. I'll do it with a separate map. Instead of trying to take the actual polynomial and mathematically reduce it, which I don't know how to do, I'm not good with polynomials, I'll just stitch together a bunch of different clues and tricks and hacks and whatever I can put together somehow to try to just make it work. You know, getting something which works now is better than getting a grand idea 10 years from now. So I want to list essentially 6 different tricks, or 6 different clues. Each clue inspires a little trick, and you put these together, and it seems to work. It's not a proof. I've only tested it on one kind of data set. It was a toy data set to start with, but that's as far as I've gotten. Maybe you can improve on it for me. So this is odd. This is very odd, because I don't see the other part of this. Oh, okay. I think I know what's going on. I'm going to start with a very simple example, which is just a 2-dimensional case. So, you know, I illustrated 100 pixels going up to 10 dimensions. I can't graph 100 by 10. I can't graph a 1,000-dimensional space. I'm going to do the absolute minimum, which is a 2-dimensional input space graphing up to 1 dimension of output, because I can barely fit 3 dimensions on a slide. I hope you can grant me the literary license for that, because this way I at least get to draw pictures and make them understandable, even if it's nowhere near the complexity of the real problem. So let us suppose that we've got this 2-dimensional input space, and we've got something approximating a 1-dimensional motion in it. You know, some little pixel is wandering, or somebody's little light, flashlight image is wandering around on this it's not even a pixel array, it's just 2 dimensions, and you've got something which is kind of going in approximately a circle. And that's our input, and we want to learn how to figure out where the input is, how the input is changing, how to predict what's going to happen next. We basically want to make a prediction, and then somebody else can use a prediction. We're just going to try to figure out how to learn the pattern and how to predict the pattern. So it's a graph from 2 dimensions into 1 dimension. So here we are. It has found it, according to this recipe somebody else invented. It has discovered sort of the contours and has found there is this function which you and I happen to know is x squared plus y squared, or x1 squared plus x2 squared, and that function happens to be nearly constant. You know, so even though x and y are flailing about, x squared plus y squared is kind of on a circle. That's good. That's what it's supposed to do. So what we have at this point is we have the map up from 2 dimensions to 1. We have the forward mapping. we don't have the backward mapping. We don't know how to find x and y given x squared plus y squared, and that's what we want. So this, in a nutshell, is what I'm trying to work through. So I've got the 6 different tricks, some clues about what we've got and how to use them. And let me just walk through those. So the first clue. The input data we have is not filling all possible values. It's on what we'll call a manifold, a locally low-dimensional subspace. In this case, let's call it approximately a circle. So most possible data points are not used. This is good news. We can use that. So the way to use that is to find some way of representing those. Now, we happen to know it's a circle, but in general, it may not be a circle. It may be a pretzel, it may be a line or a triangle or something else. So since we can't designate the shape, all we know is it's something low-dimensional. Let's take a bunch of sample points, the red ones I'm going to call anchor points, and plop them around. Think of them as cluster centers. We're going to do a cluster analysis on the input space, drop a bunch of clusters down. I happen to be fond of k-medioids. It's better than k-means, leaves out outliers better. So we find some cluster centers on the input space, and that's where we're going to focus our attention. Okay, this was the first trick. Second trick, kind of like the first trick. You notice that about in the region of any one of these cluster centers, the data is still low-dimensional, which means it is not a given fog in all dimensions around that cluster center, but it's stretched out in this case, one dimension, ideally just a few. So how do we represent that? I would take the covariance matrix, the eigenvectors of the covariance matrix of the data about that cluster center, and notice that it's stretched in a particular way. So I'll just write those eigenvectors down somewhere, and that will help remind us in what way the data is oriented about each cluster center. So now we've got a reasonable representation of the low dimensionality, the locally low dimensionality of our input. We're getting there. Clue number 3. We've got the smooth function. It's in this case a second-order polynomial, but it's not a really wrinkly function. Nice thing about smooth functions is they're locally linear. So around any one of these cluster centers, we can do a reasonably good job of approximating the function by saying it's linear, Taylor series. So that's what we'll do. About each one of these things, we'll look at the polynomial, we'll find the gradients about however many dimensions it has, and we'll write them down. So we'll have, I'm calling S sub L. It's going to be the linear approximation about that cluster center. So we're getting there. So we not only know where we care about the data, we know something generic about the function in the neighborhood of each one of those points. Halfway there. We're through clue 3 through 6. Let's go to 4. Well, we can't go to 4 yet. The good news is that we have this locally linear function, and linear functions can be inverted. The polynomial we were talking about can't. That sucks. And if it were an arbitrary function, that can't either. But linear functions, yeah, you can invert those. It's just a matrix. Well, pseudo-inverted anyway, since it's going from a low dimension to a high dimension. So when you pseudo-invert it, you basically get the best guess linear inverse, subject to like a norm constraint. The problem here, that is a good news, bad news story. The bad news is that when you get that pseudo-inverse, it does indeed tell you a point on the high-dimensional manifold, or the high-dimensional space, which solves this equation, or solves this inverse equation. It does not tell you a point on the manifold you care about. Remember, this linear function doesn't know about the fact that these little points are in a little stripe through the red point. The linear function just tries to pseudo-invert, and so it's going to aim somewhere off to the side. It's not going to put a point back where you want it. And so we've got to get a hack around that. So this is where we use that covariance matrix. And if somebody's really clever, they can find out how this is a hack and not the mathematically perfect thing to do, but I'm not going to tell you. The trick is we have the covariance matrix, which tells us how the manifold is stretched, where the data actually is in the neighborhood of that red point. And so the trick here is first you get what singular value decomposition tells you. You get the pseudo-inverse, so you're now down somewhere on the original data space, and you use that covariance matrix to stretch it out. So if the linear inverse gives you that little horizontal green line there at the left, you stretch it and it's going to become much more like the diagonal green line on the right. It's not perfect, but it's a pretty good job, and it's numerically fairly stable. So this is a way of, at least approximately, getting your point back onto the manifold you care about. Now, obviously, you have to throw in a normalization term here so it doesn't get too far away. But that's not too hard. So now we've got a way of actually starting with the low-dimensional thing and getting our way back down. This is good. Almost. There's one thing I left out. Another good news, bad news. The good news is that trick I just explained works, of taking the locally linear function, going back down to the manifold, stretching it. That all works if you know which point you're starting with. But we don't. We just know how high we are on that sheet. We have, in this case, one dimension of input. We know we are on this one-dimensional space. We want to get into the two-dimensional space. There are lots of different points on that one-dimensional space, and many of them share the same value, even though they're far apart. You can imagine, like below, perhaps all three of those boxed-in anchor points happen to share the same elevation on this hill. They share the same value of the number we're starting with. How do you know which one to choose? This is a big problem. This is where it becomes an ill-posed problem, because there can be many such points. And you have to somehow choose which of these red points to start with if you have any hope of getting to the right neighborhood when you're going backwards. So here's the clue. Well, first a restatement of the problem. We certainly need one of these red anchor points which shares the right low-dimensional numbers. It has to be the right height on this. So we're starting with that. So that's necessary but not sufficient. But we somehow need something to break the logjam, to break the tie, if there are many such candidates. We need a hint of which ones to use. And the good news is that we're dealing with some sort of input space which is supposed to be continuous, which means whichever red point, roughly, it means whichever red point we used last time is probably close to the red point we're going to use this time. It may not be the same, but it's not going to be on the other side of the circle. So we've got two complementary hints, one which tells you how high the red point ought to be, and the other tells you where it ought to be, in what neighborhood it ought to be in XY space. So we've got, even though neither one of these alone is sufficient, they're at least sort of orthogonal, they're not the same thing. So maybe we can combine those hints, sort of do a best of both worlds approach, a compromise, and maybe that will narrow down which one of these red points to start with and this, which linear function to invert and so forth. Okay. Oh, yeah.
So, just to try to help my understanding, if you had a perfect circular motion and you were doing this problem, then you wouldn't be able to use this, is that correct? Because every
one of the problems, okay, here's a digression, a very good one, about one of the problems with this method of analysis is I'm borrowing this thing called slow feature analysis, which looks for quickly changing things and finds some constant, or some not constant, but some less quickly changing function of them. Now, that's a very good idea, because in the long run, you want to get away from things which are changing quickly and find things about the world which are more constant. But the extreme version, you don't want to find something which is so constant as to have no information. So that is not, I would say, even a fault of his approach. It's a fault with our understanding of what we're trying to accomplish here. You know, you do not truly want to find things which have no information content whatsoever. You want to find things which have a little information content which is really useful. Like, is this a dog or not? Is it going to eat me or not? But not something which flails minute by minute. So that is an extremely deep question. And because it's a deep question, I can't answer it with an algorithmic answer. That's why I said at the beginning, let's just assume this thing is approximately a circle. I am literally trying to sidestep the extremely deep question of what constitutes a useful invariance. What is the huge difference between slowly changing and not changing at all? And I'm just trying to give an example which illustrates the process here. If you're dealing with real pixels, it isn't a problem. Nothing in the real world is going to be that constant for you. Okay. So does that answer your question? Is that good enough? All right. Feel free to follow it up later. There are a lot of deep questions buried in this. Okay, a final clue trick pair, which is not essential to solving the problem, but is very useful in evaluating your solution, is you've still got a sense of where the data is supposed to be, and you've got a putative data point. And you can tell if you're doing a good job, in part, by whether the data point you get, one of these green stars, whether that data point happens to be close to the points you've gotten historically. And one way of doing that is to take these covariance matrices, which tell you, roughly speaking, where the data is near to the red circles, and using it to create Gaussian hyperellipsoids, which is basically a way of making little probability clouds. And now you can tell if the point you just got, the one you are claiming is your prediction of the future, if that point is in fact inside one of these little probability zones or not. So it's a hacked way of getting a kind of probability number as a sanity check. Worst case, you at least know that you suck. You know, sucking isn't that bad if you know you suck. The worst thing is if you suck and you don't know you suck. So this is kind of halfway there, and it helps correct the problem. So here, let me just walk through this whole thing. The whole bunch of these steps here is kind of a cartoon reminder, and then I can show you a very simple test case. So what we want is we want to find the green star. We've got a history of these, the last blue black dots. They seem to be moving in some pattern. We want to know where they're going to be next. We want t+1, which we have not seen yet. So the first thing you do is you find this slow feature, this invariant or nearly invariant polynomial of the x's. And so now you've converted it from a two-dimensional thing, which changes quickly, to a one-dimensional thing you hope changes less quickly as a function of time. Now, in that low-dimensional space, you extrapolate. So because it's smooth, you just hope that you can just do some kind of a linear extrapolation and guess my new value of this invariant thing is going to be up here. That's the green star down on number 2, the one you expect to get. Now you look over all of your anchor points in that space, and you find out which ones are close to that. So down here on the bottom, all the dotted lines are all the different values you could have. You know the one value you want, so you look at things whose values are near to that. And I've just at the bottom enumerated candidates 1, 16, 3, and 7. So out of maybe 20 anchor points, those are the ones which are close in that space. So just write those down, hang on to those few integers. Now you go back to the space below, the high dimensional space, and taking your most recent point there as a hint, you now look for the other anchor points which are near to it. So this is the complementary part. You're looking at nearness in the input space rather than nearness in the output space. You have a different list of candidates. Let me just enumerate them: 8, 3, 5, and 17. So now you've got two lists in curly brackets. This list from the input space and the other list from the output space, which I've got in the table. The ones where the output space, that's on the left, that was 1, 16, 3, and 6. And on the input space, 8, 3, 5, and 17. And you do some kind of a best compromise and say, guess what, 3 is on both lists. Exactly how you do this is just another hack. I even forgot how I did this one. I think I just did something where not so much the sum of them are the same, but it's like the sum squared is minimum or something. So you basically try to find things which are high on both lists, and the first thing which is high on both lists wins. So you take them both into account somehow. Now you have an anchor point. Now you know which red circle, and it's all home from there. So you use that particular red circle. So you've got now some input point which is close to the red circle but not on it. Or no, you don't have the input point. You have historical inputs, but you have that thing. You try to find how far away from the red circle you are up in output space. You project it back with the pseudo-inverse. You project it back and now stretch it out along the manifold, so it's now presumably where you've always seen your data. And then you take that stretched bit and actually tack it on to where the red point is, so it's now stretched relative to the red point. This is all Taylor series, basically. So we're now back to our input space, except now we have a prediction of a new point which we've never seen before. We think this is where it's going to be based on historically where we've seen the points, what our recent trend extrapolation has been, and then all this pseudo-inverse stuff. This is basically it. That's what we've done. And I wish I could say that I tested this on real-time video images or something like that, but this research I was working at an institute which closed, and this research problem got just about to this point when the institute closed. So it's been sort of staying in stasis for the last few months. But let me show you the amount I was able to prove, at least to my satisfaction, that the concept seems to work. There are two parts to the test. The first is testing the part that I didn't do, and that's the slow feature analysis. Does this system for finding stable patterns in an unstable line of inputs? Does that actually accomplish anything sensible? Which means we need to start out with an input space which is simple enough that we know if it makes sense. If I was doing real-time images, we don't know what the answer is, so it's hard to check. I want something better than that. I want to know what the answer is. So it's, again, an absurdly simple space, and it's pretty good for illustration. The second part, after proving that I've learned the upward map properly, is to see whether the downward map actually is a good method of prediction. And my answer is it's 95% good. So let me show you that. The first part, look at the bottom first on those kind of black lines. The input space is 20-dimensional, reasonably high, more than the 2 I showed you. And all we've got on there is blurs, a little Gaussian blur moving sideways with circular boundary conditions. So it goes off here and it shows up over here and it just goes round and round and round in one direction. And so it just keeps moving sideways. I think it's 3.3, a third of a pixel per step. And there are 3 different widths. So there are 3 different patterns. We can have a narrow Gaussian, or a medium Gaussian, or a wide Gaussian. Just like Goldilocks and the 3 berries. You've only got, big, medium, and small. And they just keep spinning around here. This is a truly 2-dimensional problem. So even though we've got 20 dimensions of retinal input, the only underlying parameters generating this are where it is, that's the 1 dimension, side to side, and how wide it is. So the true intrinsic dimensionality of the problem space is 2 dimensions, and I want my system to discover that 2-dimensionality. And if it does, then I am confident that the forward system worked and I can worry about inverting it. So let's see how it did. These 2 graphs are the 2 main dimensions that it found, the 2 main polynomials it found. The one on the top seems to correspond to what? Because I was running this thing time and again, and I changed the width of the Gaussian, and the top parameter has 3 discrete values for the 3 discrete widths of Gaussian I found. Now this top parameter is a polynomial of 20 inputs. So it's got 20 inputs, and it's a second-order polynomial. I do not know what the coefficients on this are, but there are about 400 of them. So it is not some puny little thing. It is actually a big, ugly function. But whatever that polynomial is, it seems to be reasonably constant at 3 reasonably different values for the 3 different widths of the Gaussian. So in some sense, it has discovered as much as you could hope for about the intrinsic nature of which one is of wideness. It turns out I varied wideness. I didn't tell it. It figured it out. The bottom graph seems to have discovered the one other thing which changes slowly, and that is the position of this moving Gaussian blur. Because you notice, oh, by the way, the red points are the data of the polynomial. The green points are the generating function. So on the top graph, the 3 step functions of green are the generating parameter I gave it in Gaussian width, which I think were about, 50% off each. I didn't scale it right, I'm sorry. So you can tell that on the top graph, the where or the what, the Gaussian blur widths in red, which are bouncing around, are at least changing at the same time as the actual width of the Gaussian, given in green. The bottom one, the actual position is again given in green, but it's now the sawtooth pattern. And the polynomial discovered something which is a 1-to-1 correspondence to that sawtooth pattern, which is a sine wave. You wouldn't really expect a polynomial to get a sawtooth. It's hard to get polynomials which change discontinuously like that. So I'm quite happy with the sine wave, because the sine wave is something like telling you the cosine of the position of this thing. So roughly speaking, the red which came out of the system are the 2 parameters I learned out of the 20 parameters I could have learned, and they correspond very well to the actual generating parameters I built into the system. So this is supposed to stand as, if not proof, at least plausibility, that the system for discovering intrinsic, slowly varying features works. That's part 1. Now I'm going to show that my system for going backwards also works. So that's the next step. Does my little hacked up map of these 6 different clues and tricks and covariances and anchors and all that, does that actually learn to predict what the next picture is going to be? So this system has just learned, it's seen a bunch of Gaussian blurs moving by. Now I'm setting it up to try to figure out where these pixels are going to be next. based only on its own learning, no supervision or interference or hacking of any kind. So let's see what happens. Let me kind of restate the problem. We now have a lot of history of learning things back and forth, and we have a handful of recent points in this high-dimensional space, which correspond to a blur moving sideways. And where those question marks are is where we want the system to come up with an answer. We want it to say where the white and black is going to be in place of those question marks. But what does success look like? I mean, is it success relative to zeros or ones or what? I'm going to use the weatherman's prediction, which is the null hypothesis is that you're merely predicting the future is like today. You're merely taking as a reference whatever your most recent actual data was. It would be really stupid to do worse than that. So I've gotten a metric where you get a 1.0 if you merely make as your prediction what your most recent data point was. Anything below 1.0 is good. So the error is going to be normalized such that 1 is the reference prediction and 0 is infinitely perfect. And so you imagine I'm going to show you a graph with a bunch of things below 1. Here they are. Reference prediction is a dotted line. Some of the points are really bad. They're 3 times worse than the reference prediction. Most of them are not. Most of them are at about 5%, 6% of the reference prediction, which is, I would say, 95% good. And that's without using my little trick of figuring out which points suck and which points don't. If you use that probability estimate with the Gaussian hyperellipsoids to figure out whether a prediction makes sense based on your priors, you can now decide to exclude the ones which, on that basis, don't look good. So this is not post hoc exclusion. It's not looking at whether it worked and then saying, oh no, I'm going to throw that away because it sucked. That's cheating. It's in advance deciding whether you're going to throw it away. And if you filter off by the median there, you've now got twice as good. So now it's 97% good instead of 94% good, which is, as far as I'm concerned, for a first iteration of a hacked up algorithm, as well as I would expect an approximation to be. But again, this is supposed to be a sort of a Wright brothers biplane to the problem of learning data compression and unfolding it again. It is not the last word. I'm sure there are a million other ways to improve on it. Oh, by the way, I wasn't tossing median. I wasn't tossing 50%. I was only tossing 20%, so it's much better than I thought. How about that? So here's sort of the punchline. First of all, it is possible to not only find, but to invert these slow features from high-dimensional space. They can be used to make specific predictions in time, predictions of the future, not merely reconstructions of the present or the past. The prediction works well at the 95% level, and it can do even better than that if you use built-in confidence estimates which come with the territory. So that's really all there is. I started off, this was kind of a bait and switch. I started off with grandiose proposals about how our brains work and how great this will be for sort of society and philosophy and stuff. And I've ended not even with mathematics, but with a string of mathematical and programming hacks. But that's the way I know how of getting from here to there. And I'm hoping maybe some other people will have some better ideas or be able to help out. That's it. Thanks. Yeah?
How do you predict motion in time? This model seems to just, I mean, in the real world, if I saw somebody moving at half the speed that I'm used to seeing, then I would notice. How does your model deal with time?
Let me try to repeat that for the sake of the microphone. How do you predict motion in time? Because in the real world, you see things actually moving, and you sort of know where they're going to be. Is that your question?
Yeah, but if things move faster or slower than I expect, I observe them. I have a sense of time. Your model doesn't, I don't know how it captures.
Oh, very good. Oh, this was a wonderful question. How do you predict motion and time? Because he observes that this model does not really have a sense of time. Well, in some sense it does. When I said you're extrapolating, you take the most recent values of the pixels, and then at the next time step you try to put a slope through that. So given the most recent history, you actually can, in this case you do, make a prediction of where the thing is going to be. So in that sense it does, but there's a deeper sense in which you're absolutely right, and you've discovered one of the very weak points of this whole thing. I told you that this slow feature principle, not the one which I'm borrowing wholesale, finds a polynomial function of the inputs at one time, and it creates a polynomial which happens to change slowly based on historical statistics. You're right, that polynomial is not a function of multiple time steps. It is a function of now only. It happens to be a similar polynomial to the one here and the one here, but the polynomial is not multiplying x of t times x of t minus 1 times x of t minus 2 or something. It is not capable of nonlinear interactions across time. I would regard that as a weak point, and one of the things I would like to do is fix it. An obvious way is to just expand the dimensionality it's capable of learning from to a handful of time steps at a time. So you're right, this polynomial system does not detect motion. The polynomial system by itself has exactly the same value whether you're moving to the left or to the right. And that's a weak point, but it's, I think, easily hackable. There's nothing intrinsic about it. Fortunately, my inverse process does not depend on that particular trick of the polynomials. My inverse process is a pretty generic one. So I'm impressed. I'm glad you reminded me of that because I forgot to say it. Yeah.
So a lot of, the problem you've decided to attack is really good, right? Inverting the thing is really important. The inversion doesn't always happen when you're observing something and predicting what's about to happen. In the brain, you also need to invert the typical stuff when you receive top-down input from some higher process. So if I tell you, think of a picture of your mother, that goes up the auditory cortex and then back down the visual cortex with no prior picture of your mother that the one you're about to imagine is only a slight change of. So, is that outside the realm or scope of what you've done, or how would you, because at least the one step explicitly made use of the previous point. Although it didn't seem like you could, it seemed like there were probably other ways to do that step that didn't require that.
And just to echo Andrew's point, there were some experiments that did this.
Is there any chance I can get to this question before we expand it? Because it's a very good question, and I want to focus, if only before, because I might forget otherwise the nuance of it. It's an extremely good point, and I just want to get to it. I will get that. To rephrase the point, in case Mike's didn't pick it up, and in case I misunderstood it, the system I've outlined makes its prediction both by appealing to the abstraction, the sort of the low-dimensional version up here, but also by appealing to the recent past in the high-dimensional space. In a real brain or in a real machine learning system, you may not have access to a reliable form of the recent past. You may not have access to a high-dimensional hint. You may only have the abstraction to work from. Is that a fair condensation of it? Absolutely true. Part of my plea to this is that I was trying to only work of what happens within one module. So I was explicitly not talking about how modules talk to each other and how one of these compressor modules would take advantage of some prior it would have. Certainly in an actual brain, including the hierarchical thing I outlined, these guys are talking to each other all the time. Each one of these things is not only looking at its most recent version of the abstract variable and the past, it's also looking at all the votes coming down, raining on it from above, from all the people at a higher abstract level who are now giving him their opinions, their Bayesian priors, of what that abstract variable is going to be. So the good news is that you have a much better version in such a system like a real brain, a bias in favor of a picture of your mother as opposed to George Bush or a bicycle. The bad news is that since you don't know how any of the pixels are lined up, you don't have the high-dimensional hint. So first of all, I can't claim I've solved that. I've got some ideas on it. But you can see that at least you've got half the hints. If you've got some prediction of the system, it won't give you the exact specific prediction. If you know you're going to see a picture of your mother, but you don't know where it's going to be in pixel space, obviously you can't say you know which pixels are going to be black and white. However, you are now primed to much more quickly distinguish whether it's your mother or not, because you have now, in some sense, restricted your search space to those which are consistent with mother versus those which are not. I know that's a kind of a hand-wavy approach, but does it at least address your question even if it doesn't answer it? Okay.
You can go back and forth, but I'll let
Okay, all right, that's as good as I think I can do with that question now. But it is a very good one. Yeah?
And what's the error of my question, so we can take that?
Oh, okay, cool. So I wound up answering the question which wasn't asked better than I answered the question which was. Lucky. Yes.
So going back to the question of the computing the inverse, I really liked your analogy of you compute a function and that sort of, you have it and then you need to re-invert it and you need to discover this function. The question is how accurate does that inverse need to be? So if you take the example of you drawing a circle, my looking at it and my building a mental model of a circle, and then I copy your circle. For something simple like a circle, I may produce a perfect copy, but if you draw a picture of a dog, the picture of a dog that I draw might look significantly different. Right? So at what level, how accurate does that inverse have to be? That inverse function that our brain is computing.
All that the inverse let's see, to rephrase the question, I've drawn a very simple mapping system from very few dimensions up to even fewer and back again. So you can reasonably expect that the two are going to line up fairly well. But if the problem is much more unconstrained, much higher dimension, how can you tell whether you're doing a good job, and how can you even expect that you might be doing a good job? Is that a fair?
Well, no, the question is how good does the inverse need to be for the brain to be able to reason effectively about the picture of the dog?
Let's see. How good does the inverse need to be in order for the brain to reason effectively about the picture being a dog or something like that? It depends on which. I'm, of course, dealing at the level that might apply for a mouse. So when I say reason, I'm really thinking of just being able to fill in the blanks and kind of recognize what it is. But the short answer is, to the degree that you have sufficiently narrowed the probability space. To the degree that you now have a prior which is going to help you quickly figure out whether this is a predator or not. You know, if you've weeded out 90% of the possibilities, you're in principle 90% fast, or 9 times faster at evading the dog, something like that, rather than having to sit down and wait and gather more data to figure out if it really is a dog. So any improvement is good relative to a baseline of nothing. So it's not a system which will presumably catastrophically fail if you've got more error than you're accustomed to having. It's merely going to have to gather a bit more data or process it a bit more. But then again, I'm completely leaving aside from here the questions of how these different modules in the hierarchy work, and whether this system has now got 50% of a dog, so it passes its 50% up here, and this system passes its 50%, and they go up, and now you've got 100%, and that guy goes, and now these guys are at 70, and now these are at 90 or something. You can imagine, although I'm not specifically outlining, you can imagine a system in which the reverberation up and down is a settling process. So even though each individual piece has very noisy data, and by itself does not have a very good estimate, each one is iteratively improving the estimate, passing it on to other levels which have access to more information from other places, and that collectively they might be able to settle toward or zero in on an answer that would be hopeless for any one of those modules independently. Okay, I'm seeing a time marked here, so it looks like I've run out of questions just as they're getting hard. Thanks an awful lot for your time, and I hope you guys solve this for me. Take care.